Hi guys, so in today's video we're going to take a look at exponential functions. An exponential function is one in which the variable, in most cases x, appears as an index in the function. Here we can see a few examples of exponential functions. So we've got y equals 3 to the power of x, a function of t equals 2.7 to the power of t squared plus 4, and the final one, Tn equals 3 times 2 to the power of n. And hopefully that last one looks very familiar, and we'll actually talk about the connection between exponential functions and geometric progressions more in just a moment. We will only be looking at simple exponential functions, which always take the form y equals some value a times another value a to the power of x. So let's take the function f of x equals 3 times 2 to the power of x. This is a simple exponential function, and we can see that f of 1, so the function at x equals 1, is equal to 3 times 2 to the power of 1, which is 3 times 2, which is 6. The function at 2 equals 3 times 2 to the power of 2, equals 3 times 4 equals 12. The function at 3 would be 3 times 2 to the power of 3 equals 3 times 8 equals 24. And we can see that we've got in our answers a geometric sequence. Starting with 6 as the first term, we've got 12, 24, the next one's going to be 48. And this is because all geometric sequences, the explicit formulas for them are always exponential functions, simple exponential functions. However, the difference with a general exponential function and a geometric progression is that a geometric progression only exists for integer values of x. Okay, or as we normally name it, n. So you can only evaluate the function at x equals 1, 2, 3, 4. In a general function though, we can say, well, what is the function equal to at 0.5? And we get 3 times 2 to the power of a half, which is 3 times the square root of 2. So a function exists for all possible x, whereas our geometric progressions, which are also simple exponential functions, only exist at the integer values. So they are a sequence of values, which is actually still a function, but our general function exists for all possible x. If you were to graph the values in a geometric sequence, you would get a graph that looks like this. So at your first term you have some value, second one say you might have twice that value, at the third it's doubled again, fourth doubled again, fifth doubled again. If you were to take the function though that represented the geometric sequence and evaluate it for all possible x, then you would have a general exponential function that was of the same shape but continuous. So it now exists for all possible values in between the integer values that make up the geometric sequence. So we'll recall that our basic simple exponential function has the form a to the power of x, and we can consider two broad types of these functions, and they have different shapes. The first is when a is greater than 1, and we know from looking at geometric progressions that these are the types of sequences that diverge to infinity. And we see the same thing in the graphs. If we graph out a function that has a greater than 1, then what happens to the values over time is that they get larger and larger and larger. On the other hand, if we have a less than 1, then what we get is a graph that looks like this. We'll start with some value, and that graph will get smaller and smaller and smaller over time. The interesting thing to note about these functions is that they always asymptote, so they never reach 0. The other thing to note is that when x equals 0, a to the power of 0 is 1, so this value here at the intercept is always equal to whatever your value of capital A is. And this is also known as your initial value.